Good morning. I hope this finds you doing well and staying warm. We are going to continue on chapter 15, and today we're going to talk about a buffered solution. We have buffer solutions in our body. Our blood is a very good buffering solution. Our urine is a good buffering solution, and it is something that resists change in pH. It's really important in our bodily systems to not have a pH change because that's one thing we know that we are starting to get sick or further diseases happening. A buffered solution may contain a weak acid. So notice I did not talk about our stomach acid because that's a very strong acid, so it's not really a buffering system. Containing a salt and its weak base and another salt containing the weak acid. So here I have a buffered solution contains a weak acid, 0.5 molar acetic acid. We should recognize that that is a weak acid, and we need to really memorize again those 6 strong acids because you need to know if this is strong or weak. We also get the indication of that because of the very small Ka. And then I have a salt, sodium acetate. Sodium is the metal to the nonmetal, so we know that that's an ionic bond, and it wants us to calculate the pH. Notice we don't have the symbol here for acetic acid, and I put that in here, and you can see that I just wrote HACET because it doesn't really matter. You might have situations where they just say to use the generic formula for acids too. For all of these, we can just say HA at equilibrium with the hydrogen ion plus the anion. So either of these will work. We don't need to know the symbols. We just need to know that it's going to dissociate. So you can see here that I have 0.5 molar. I've added the common ion here is the acetate, so I have another 0.5 molar. The sodium is the spectator. I do not know my hydrogen ion concentration, so that means it's going to shift to the right according to Le Chatelier's. I have a very small Ka, so I've crossed off the X's, and I went in and I calculated my pH. Now in AP, they are really taking a look at whether or not we understand what is in our beakers. And so if we think about what's in the beaker, we have our acid here because it's a weak acid. It's not going to fully dissociate, so you do need to write it as a compound staying together. It is going to dissociate some. We have our spectator ion, and we have water. There's lots of times that they'll ask you to identify some sort of drawing like this, or you might have to draw it yourself. Okay, so we also have a shortcut called Henderson-Hasselbalch, and this equation is on your AP reference sheet, and what it simply says is we can use this in buffering situations. That pH is equal to our pKa, so the log of our Ka, plus the log of the root of the acid over the acid itself, or the conjugate base over the acid. So you can see I just substituted everything in. The negative log is equal to the pKa plus the log of the base over the acid, and I got 4.74, exactly the same. Now, it doesn't matter which one you use. If you are confused about when to use this because you're not sure it's a buffering situation, you can see that ice works every single time. Okay, so here's another one that we need to take a look at when it isn't a common ion that's being added. So I have the pH of 0.01 moles of solid NaOH. You can see that that's a strong base, so I know it completely dissociates, and my Na is a spectator ion. So when I look at my OH and I look at my original equation that I had, my original equation again, remember, was that I had the HA, and I had the hydrogen ion, and I had the anion. Well, that doesn't look the same. And so this is an HA, goodness. And so I have to take a look at when I add my base, my OH, that OH is combining with the hydrogen from here and making water with this hydrogen. So this is the correct equation. Now, when you, as I've been talking to you about always, is that when you are given a certain amount of both reactants, I need to think limiting reactant. So it tells us, I don't know the concentration of it, it tells me that I have 0.01 moles of my sodium hydroxide. So I have to find the moles of the acid before I can even start. We need to always remember that molarity times volume gives me moles. Well, when I look at this, this is 1 to 1 to 1 to 1. So that means that this is going to decrease by 0.010, It's also going to decrease this one. And so I can see that this is all used up. It's going to be my limiting reactant. If it's decreasing by 0.01, that means it's also increasing on the other side. We are still ignoring water as we have been doing all along. Now, I could use ice, or I could use my Henderson-Hasselbalch equation because I recognize that I have a base and I have an acid. So I can take the negative log of the Ka plus the log of the base over the acid. And I see that by adding that 0.01 moles of a very strong base, my solution hardly changed. So this is a very good buffer. Again, take note of all the species that are listed in water. So how does it work? How does a buffer work? You have to have a weak acid or a weak base. They are able to absorb a lot of ions. If we have a strong acid or a strong base, they're not going to buffer because they fully dissociate. We need to have a significant quantity of a common ion. Obviously, if I have too much of that common ion, it isn't going to be able to buffer. I gave you an example of our blood as a good buffer. Well, blood has only a certain point that's going to allow it to continue to buffer. When those hydroxide ions are not allowed to accumulate, again, we can talk about even that it's a very strong base being added. If they're not accumulating, it'll continue to buffer. Well, what's the best situation is when the ratio of my base to my acid is very similar and the pH is small or equal to 1, then I know I have a good buffering situation. All right, so I have another just example here of a common ion. Go ahead and look through that and make sure that you can understand that. It's just another example. And then down here in the summary, you can read through all of these, the different types of buffering situations. Go ahead and annotate that or make sure you have some good pictures of what all of that means. Okay, all right, that's it for 15.2.